So first of all, we start with force. So what they said here, force is the rate of change of momentum. So when you look at this definition of force, you have to think of the formula at the same time. So force equal to rate of change of momentum, which is mv minus mu over t. So that is the meaning of rate of change of momentum. Okay, so second point, finding resultant. So to find resultant force, we use nose to tail. So the nose to tail over here is also known as triangle law. Triangle law in mathematics. In vectors, we call it triangle law. Okay, so example, let's say you want to find the resultant force. Okay, example here. Let's say you have a force acting in this direction, F1. Then you have another force acting in this direction, F2. So to find the resultant force, we just draw F1. Then this is the head, the nose of the force, the first force. Then you join with the tail of the second force, F2. And then from the starting point here, this is the starting point, this is the end point. So we draw a straight line. And this is the resultant force. I call it F. So we get the resultant force by using nose to tail method. Of course, when you draw this, one of the way is you use accurate scale drawing, where if this is 5 Newton, then maybe you set up your scale 1 cm represent 1 Newton, and then this is 5 cm, and let's say this is 8 Newton, then you draw 8 cm, and then you make sure the angle is correct by using protractor, and after that you draw your straight line in this to get your resultant. Then you can measure, let's say this is 11 cm, then this is 11 Newton. So by accurate scale drawing, we can find the magnitude easily, and after that you can find the direction. So the direction normally we count from horizontal or vertical. So for this case, since I have the horizontal, so I just count this angle to find out the direction of the resultant force. So resultant force, we need magnitude and direction. So if you don't want to do accurate scale drawing, then you can use trigonometry. Trigonometry is where you just form the diagram without accurate scale. You can just roughly draw out, and then after that maybe you can use SOHCAHTOA, the sine, cos, tangent formula, or even you can use sine rule, cosine rule to work out the magnitude of the resultant force together with the angle of the resultant force. So we can do that. And so let's see this case. Okay, so this is an object on an inclined plane, and going downward is basically the weight of the object. Okay, so for the weight of the object, normally it is acting downwards due to the gravitational force, and then this one is perpendicular to the inclined plane. So this is the normal reactions. So the normal reaction is like this. Okay, now let's see what they do here. So they draw the 5 Newton downward. Okay, 5 Newton downward, and then they draw the 6 Newton. Oh, if they draw like this, this is not the normal reaction. Normal reactions won't put together to form resultant. So this one, maybe I call it, let's say there is a force acting in this way. Okay, so the weight of the object is this way. Then there is a force which pull the object in this way. So the weight of the object and then a force of 6 Newton pull it in that way. So this is the starting point. This is the end point. So we have the resultant force. This resultant force means this object won't stay on the inclined plane sliding up and down anymore. But if you follow the resultant force, the object will move this way. Follow the resultant force. Okay, the object will move this way. Okay, we move this way. Okay, so the normal reaction that I mentioned just now is not this situation. Okay, it's not this situation where it won't have any resultant force. So let's say I give you another example. I have an inclined plane again. So I have an object here. So the weight is 4.0 Newton. 4.0 Newton, let's say. 4 Newton. Okay, so and let's say here is 30 degree. I try to make it same, 30 degree. Okay, now this one, like what I mentioned just now, it is a external force that pull the object in this direction. But I also mentioned that in certain situation we have a normal reaction, a normal reaction. Fn, normal reaction. If let's say I want to find a normal reaction, because this object is on the plane, right? So there is a normal reaction. So if you want to find it, so we do it like this. We resolve the weight. This is the weight, 4 Newton. We resolve it. So we resolve it like this. So where this is the 30 degree, then this component is the component perpendicular to the plane, the component of weight perpendicular to the plane. So this is 4 cos 30 degree. So which end up with 4 sec 3 over 2. So which end up with 2 sec 3. So this is components parallel to the plane. So this is 4 sine 30 degree, which is 4 times half, which is equal to 2. Okay. Now, if let's say the object is in equilibrium, the object is in equilibrium. Compared to this is not in equilibrium. This object is going to move this way. Okay, this object is going to move this way. Follow the resultant force that work out here. It is not in equilibrium, but this object is in equilibrium. It's not moving. It's stationary. I mean, cannot. Can be stationary if there is a particular friction that act in opposite direction. So it can be stationary. So if this object is in stationary, then you can find the normal reaction by using the equilibrium concept. So the normal reaction is equal to the 2 sec 3. So then you can find out if the object is in equilibrium, then the normal reaction is equal to 2 sec 3 Newton. So that is what I trying to say just now, because when I first look at it, I feel like this is the normal reaction, but in fact it's not. It's an external force that act on it, making the object move this way at the end. Okay, so that's the difference. You see, the normal reaction is supposed to be 2 sec 3. 2 sec 3, I think, is just maybe around 3 only. But this is 6. This is obviously not the normal reaction. Okay, now let's move on. The next point, forces on masses in gravitational field. Gravitational field is a region of space in which a mass experiences an attractive force due to the presence of another mass. Due to the presence of another mass. So what idea is this? let's say, for example, I start from something big first. If you have the sun and the earth, so the sun and the earth are attracting each other because of the gravitational force. So they attract each other. So that's why the earth can orbit around the sun, okay, because they are attracting each other. So that is one case, gravitational field. Okay, now let's come back to an object on the earth. Let's say this is the earth. And let's say you are standing on the earth. Okay, so what happened here is there is also gravitational attractions between you and the earth. You and the earth. Huh? So we have to say that the earth is attracting you, and at the same time you are attracting the earth. We have to say it in that way, although you may feel weird to say that you are attracting the earth, huh? Because you are too small compared to the earth. But in fact, both are attracting each other. Okay, so we must have mass for two of these to create the to form the gravitational force. Okay, so that's why they must have the presence of another mass. So the mass of the earth and the mass of the human being, they are attracting each other. So this is just the concept, but you will learn this again in A2. So it's details. Now it's just roughly first. Okay, next point. Forces on charge in electric field. Regions of space, and so they are trying to let you understand the electric field. A region of space where a charge experiences an attractive or repulsive force due to the presence of another charge. So you can see, just now the gravitational field need another mass. That means you need two masses. Now electric field, you need another charge. That means you need two charges. Okay, so this is something which is should be more familiar. For example, if you have positive charge and positive charge, so they will repel. So if you have positive charge and negative charge, then they will attract. They will attract. Then we draw the electric field in this particular way, something like this, positive to negative. So like that, and so on. Okay, where negative, you have to draw your arrow into the negative charge. So if they repel, then you have to draw this particular way, away from each other. Okay, something like that. Showing repel. So if they attract, then you can see connection between the opposite charges. Okay, so that is electric field. And again, we will learn this in details in the later chapters in AS. Okay, now let's move on. We try to understand different kind of forces. So we have the gravitational force, we have the electric force. Now we have the upthrust, an upward force exerted by a fluid on a submerged or floating object. Okay, so that means it is the upward force that makes the object float. That makes the object float. So of course, we will learn this in details very soon in the next two subtopics. So you will learn that upthrust. Okay, so for now, you just remember upthrust make the object float. Okay, so short example for now. Let's say if you have a boat which float at the on the seawater. Okay, float on the seawater. Okay, so now this is the part which the boat is under the sea level. Okay, so you want to find the upthrust. Then you have to find for this particular space where the boat is under the sea level, it has a particular volume. So you use the volume here to find out the volume of water that are occupied by this, and then you change it to weight of water. So we call it weight of water displaced by that particular volume. So the weight of water displaced is the upthrust. So just for temporarily, we take it like this. Of course, you will see in details very soon on upthrust. Okay, origin of upthrust, pressure on bottom surface more than pressure on top surface. Force on bottom surface more than force on top surface. Resultant force is upwards. Okay, so for this part, let's see one example to understand this better. Okay, imagine this is the water. So you put an object like this below of the water. So I draw a cube. Okay. Pressure on bottom surface. Okay, so of course, to find the pressure, let's say I consider this region, the bottom surface. I consider the center of the surface. So the center of the surface is at the depth of, let's say, H2. Okay, so because of this H2, it forms pressure. So we use the formula of pressure, P equal to H rho G. H2 is the depth to the bottom surface. Rho is the density of water. G is 9.81. Then you can find out the pressure on the bottom surface. So this is pressure on the bottom surface. Okay, so at the same time, we need to know the upper surface experience pressure also. So let's say this is the upper surface. I take the middle of the surface, and let's say this is H1. Okay, so the upper surface is at the depth of H1. So I count the pressure that are pressing the upper surface. So I use P equal to H1 rho G. Okay, let's say I make it different. This one I call it P2. This one I call it P1. So you want to find the P1, the pressure on the upper surface, on the top surface. So we take the depth, multiply with the density, multiply with 9.81. Then we get the pressure on the top surface. Okay, then after that, we also need to know that the pressure is force over area. The area at this area. Okay, so likewise, this is pressure, which is equal to force over area. Okay, now based on the inequalities here, they said pressure on top surface is greater than pressure on bottom surface is greater than pressure on top surface. So that means we have P2 more than P1. Okay, P2 more than P1. And then after that, we have F2 over A. F2 over A. Of course, P2 more than P1 is obviously clear because H2 is greater than H1. H2 greater than H1. That's why that's why P2 is greater. P2 is greater than P1 because of the H2, which is greater than H1. And then I use F2 over A. This one I use F1 over A. I rub the 2 away, and not A2, or just A only. F1 over A. They have the same area for the object. So I can cut the A on both sides. Then I get F2 more than F1. F2 more than F1. And force on bottom surface is greater than force on top surface. So force on bottom surface is F2. F2 is acting this way. F2. Force on top surface is acting this way. F1. So now resultant force is upward. So resultant force is known as the upthrust. Upthrust. So upthrust equal to F2 minus F1. Yeah. So that is how we get the upthrust. So the details is like that.
What if like the top surface area is different from the bottom surface area?
Then you cannot cut already. You cannot cut the area already. So in that case, you need to find out the actual value. You need to find the actual value. So let's say for example, you have F2. Let's say this area is 2. And then let's say this area is 1. And then after that, F2 more than 2F1. Okay, so when you look at this inequality, we are still able to say that F2 is greater than F1. From this inequality, we can figure out, because this is 2 times greater than F1. So it is still greater than. So we are still able to know that F2 is greater than F1. Then you can find out the upthrust. So still able to work out somehow. Okay. Yeah.
For pressure in liquid, right? Does it like how is it exerted on the object? Like in what direction?
If let's say it's on the top surface, so the pressure is pressing down. Yeah, because of this amount of water on top, pressing it down. Okay, but if it is at the bottom, so we have to say that it is the water that presses up, press on the bottom surface. So follow the direction basically. Yeah, so that is the general idea. Okay. So there's the upthrust. Yeah. Now we look at the next type of force. So we already have 1, 2, 3 types of forces. Now the fourth one, frictional force. Force that arises when 2 surfaces rub. Okay, so I mean they are in contact. So always opposes relative or attempted motion. Okay, and then always act along a surface. Value varies up to a maximum value. Okay, so a maximum value is what kind of idea? So you try to imagine there is a formula for frictional force, which is frictional force equal to mu times R. This is the formula for frictional force for the maximum value of frictional force. Okay, so what they're trying to say here is if you have a, let's say, tar road, tar road is very rough. It's for the car to move on it. It's very rough. So it has a maximum frictional force. You want to count it, you use this formula mu times R to count the maximum frictional force. But we don't always experience maximum frictional force. Imagine you use your hand to touch the tar road. If you just touch the tar road softly, so you don't feel much much friction. It doesn't hurt your hand that much. That's what I'm trying to say. If you touch it softly, but if you touch it with force, you press the tar rod as hard as possible and you move along it. So you will experience the maximum frictional force. So that is why we have this third point. Although it has a maximum frictional force, it doesn't mean the object always experience maximum frictional force. Okay, so the frictional force may vary. Okay, so it depends on the situation. Like what I said, you touch it softly, you won't feel much friction. So if you touch it rough, with a lot of force, then you will feel the frictional force. So that's the thing.
What is R?
The mu is coefficient of friction. Mu is
AS or A2?
It is not in AS and A2. It is in mechanic. Do you take mechanic?
Maths.
Yeah, in math.
It's in A2. I know mechanics. I'm running in A2.
Yeah, in A2. So now it's like F equal to mu R is something that is not really necessary. So I just tell you what at first. Coefficient of friction R is normal reaction. Normal reaction. Okay, so we just leave it like this without necessary to know more. Okay, so now let's move on to viscous force. Viscous forces, this is also known as drag force. Drag force. A force that opposes the motion of an object in a fluid. The fluid here means liquid or air. Liquid or air. Okay, so for example, let's say we have a submarine. This is a submarine. Under the water, moving forward. Then the viscous force or the drag force is somehow like the air resistance, which act in the opposite direction. So this is the viscous force. So even in air we have viscous force. So we call the viscous force the air resistance. Okay. So in air, in liquid we call it drag force or viscous force. Okay. So its magnitude increases with the speeds of the air, with the speed of the object. So this one we discussed before. So that time we talked about free fall. So if the speed of the object is faster, then the air resistance is faster. So that is the viscous force of the air resistance. And then we have the center of gravity. Center of gravity is not a type of force. So this is just to explain to us where is the center of gravity of an object. So for example, if you have a regular object like cube, something like this, then the center of mass is basically at the center of the object, somewhere around here. Center of mass. Okay. Center of gravity. So point through which the entire weight of the object may be considered to act. So if you have the center of gravity there, then we have to say that the W is acting from that point. The weight is acting from that point. Okay, so center of gravity. And then next one. Of course, this is for regular object. We cannot expect the center of mass is always in the middle. If it is irregular objects, so we need to find out the center of gravity by using some experiment. Okay, so it's something like this. Let's say you have a piece of irregular object. You want to find out the center of mass, right? So you have to take a string, and you hang it here. So let's say you penetrate through one point here, and then you hold a string, put a bob at the bottom, then you use your pencil to draw a line, follow the string, draw a line. Okay. Now you turn the object around, and turn the object around. Let's say this same object, you turn it around. Okay, you turn it in this particular way. The same object, you turn it in this particular way. And just now you have the line already. Just now you have the line already. This line. Okay. Now you do the same thing. You put a hole here, hang with a string, and a pendulum and the bob here. Okay. Now you use your pencil to draw the line, follow the string, and then you get the intersection point. That intersection point is the center of gravity. Center of gravity. Center of gravity. So we can do something like this to find out the center of gravity. And once you get that, that is where the weight acts. So we get to know that center of gravity. Then we move on. Couple. Okay. So couple is a pair of forces which produce rotation only. So of course, to understand this, let's see one example. This one. A force push upwards, another force push it downwards. So it will make this turn. This is how we turn the steering. So you one hand move it upward and another hand move it downward. Then the steering will turn in clockwise. Okay, so this is known as couple because there are two forces which act in opposite direction but in equal magnitude. So to form a couple, it must be two forces equal in magnitudes and then parallel but in opposite directions. You see they are in parallel, this and this in parallel, okay, by opposite direction, separated by a distance of d. The d must be the perpendicular distance from the two forces. That's the d. They use s over there. So that is couple. Okay, now example one, a steering wheel in a car. So this one I explained already. So what happens is rotation happens. Okay, so this is maybe we can call this a seesaw. Okay, a seesaw with the pivot here. This is known as the pivot. So pivot is here. Okay, so if you have a force that push it downward, and let's say you don't play in the ordinary way, so you just use your hand to push it upwards, then at the end, this plank is going to rotate like this. Okay, so it move up, this one move down. So it causes rotation. Although it's just a little bit, but it's still rotation. Okay, now let's see another example. A couple tends to produce rotation only. A single force may tend to produce rotation, but it will always tend to produce acceleration as well. So we are trying to compare a couple which involve two forces as compared to a single force. Okay, a single force. This is an example. A single force from the leg. You kick the ball. That is single force, not two forces, not couple. Couple must have two forces. So a single force, it causes rotation because you kick up here, so the ball spin. But it causes acceleration also. Acceleration, the ball move forward faster and faster. So spin and move forward. So that is the difference between couple and single force. So couple, rotation only, no acceleration. Okay? So but single force, rotation plus acceleration. So you see the words here, a football baller kicks the ball, striking the sides of the ball. So you have to kick up here, don't kick the center. You kick the center, no rotation. It move forward only. Okay. The ball accelerate, but also tends to rotate in a clockwise direction. So two effect, rotation plus acceleration.
Sure, what if couple force and no acceleration?
Sorry, what is?
What if couple force and no acceleration?
Oh, why is it no acceleration? Because, you want to have acceleration, right? Based on Newton's second law, net force equal to ma. Net force equal to ma. This force is acting up, this force is acting down. They are opposite direction but same magnitude. That is the conditions to be a couple. Equal magnitude, opposite direction, cancel off. So cancel off, and the net force equal to 0. Net force equal to 0, and then acceleration must be 0. So because of that, no acceleration, rotation only. Okay, then we look at the next page. So on this page, we have top of a couple. Top of a couple. Okay, so top of a couple, the product of one of the forces. Couple have two forces, so we just take one of it, and then multiply with the perpendicular distance between the line of action of the forces. So that means torque is equal to force multiply with the perpendicular distance between forces. Okay, let's see example. Okay, so if this is the case, example 1, you want to find the torque. So based on the explanation in the notes, so we had to take one of the force, this one or this one. Let's say I take this F, multiply with the perpendicular distance between the two forces, which is the S. So then you get the torque. The torque. So of course you should expect the unit to be Newton meter. Newton meter. Okay. Then let's continue.
Can the unit be joules?
Newton meter, yes, it's joule. Same like work done, right? It's just that we seldom put joule for torque. For torque, we seldom use joule, although it is the same unit. Okay. Then let's continue. That's the torque. You see the notes here? It is worth noting that torque is a vector. If a torque that tends to turn a body in a clockwise sense is considered to be positive, then a torque that tends to cause the body to move in an anti-clockwise sense is considered negative. So it's a vector, clockwise, positive. Normally it is like that. Anti-clockwise, negative. Okay, so that is torque. Moment of a force, product of the force and the perpendicular distance of its line of action to the pivot. So a force, one force. Compared to couple, two forces. So this one force. So you want to count the moment. Let's say you take the force, multiply with the perpendicular distance to the pivot. So to the pivot, so this one. Okay. So we cannot use 25 cm, but we have to use this. We have to find out x, the perpendicular distance. Okay. So of course, in order to find this, we have to do some trigonometry. So we look at the 20 degree here. And imagine that is a right angle triangle. So let's say I draw a horizontal line here. From here, draw a horizontal line to here. So then this is a right angle triangle. Yeah, right angle triangle. So if here is 20, this is vertical, this is perpendicular, so it should be 90 degree. So here will be 70. Then here is 20 degree again. So you want to find the x, right? So basically we can just make use of the 25 together with the x. So we have the adjacent. I take 20 degree as my angle. So this is considered adjacent. This is hypotenuse. So I can use cos 20 degree equal to adjacent over hypotenuse. So I can find the x, 25 cos 20 degree. And because of that, I can find a moment. A moment of a force is equal to the force itself, 30, multiplied with the perpendicular distance, 25 cos 20 degree. And then you get a moment. Okay. Then if you count this, you get 7.05 Newton meter. So you will realize it is very similar to torque. It's force times perpendicular distance also. But the thing is, for torque, since there are two forces, the distance is the distance between the two forces. For moment, the distance is the distance from one force to the pivot. Okay, so that's the thing. We must be very careful with this. Okay, now let's say if this is how we get the torque, so we can talk about how to get the moment also. Imagine that this is the pivot. This is the pivot. If you want to find a moment of this force, so you take this force, multiply with the distance to the pivot. So this is the pivot. Okay. Moment of this force. Moment of that force equal to that force multiplied with the distance to the pivot. Half S. Half S. So you can see slightly difference in definition between torque and moment. So must be careful with that. Okay, then let's continue. Okay, we have done 4.1. So now 4.2. Equilibrium of forces. State and apply the principle of moment and so on. Resultant force, forces in equilibrium by using triangle. Okay, conditions for equilibriums. Resultant force acting on it in any direction equals 0. Equals 0. So resultant force is 0. And resultant torque about any point is 0 also. So they must fulfill these two conditions. If that is the case, then equilibrium. Okay, equilibrium. So let's say we will have example soon. We move on first. Second point. Principle of moments. For a body to be in equilibrium, the sum of all the anti-clockwise moments about any point must be equal to the sum of all the clockwise moments about the same point. Okay, so that means clockwise moment equal to anti-clockwise moment. So that is what they are trying to say. So clockwise moment equal to anti-clockwise moment. Sometimes we put it in different form. We put it in this way. Resultant moment equal to clockwise moments minus anti-clockwise moments. When it is in equilibriums, the resultant is 0. When this is 0, then this minus this equal to 0. And if you rearrange, then you get number 1. Something like that. Okay, so let's see example. Example for this case, sum of anti-clockwise moments. So which one is anti-clockwise? You assume this is pivot. And then you assume pivot is the center of the clock. So then clockwise will be like this. That is clockwise. And then anti-clockwise is opposite way. Anti-clockwise. Anti-clockwise is the blue one. So this is the center of the clock. So this way is considered clockwise. This is clockwise. This way is considered anti-clockwise. This one, anti-clockwise. Okay. Sum of anti-clockwise moment. Anti-clockwise F1 multiplied with D1 equal to sum of clockwise moments. Sum means if you have more than one force, you have to add up. So, but for this clockwise, you have only one force, one moment. So force 2 multiplied with B2 to get the clockwise moment. So that is how the resultant talk about any point is 0 works. So it's 0. You look at number 2, right? Resultant moment. Resultant moment is equal to 0 because clockwise moments is equal to anti-clockwise moment. So you minus them, you will get 0. So you get 0. So there we have 0 resultant moment. 0 resultant moment. I don't want to use talk because talk of a couple. This is not couple, so I don't want to confuse. So I use moment. Resultant moment is equal to 0. Okay, resultant moment equal to 0. Is this system in equilibrium? So actually, it depends. Let's say if this system is not moving, of course it is in equilibrium. So if let's say this plank is balanced, it is in equilibrium, then how to see the resultant force to be 0? It's something like this. Acting downwards is the F1 and the F2. Acting upwards is the normal reaction here. Normal reaction. Let's say I call it R. Normal reaction. Sometimes you see N, sometimes you see R to represent the normal reaction. Okay, so if the system above is in equilibrium, then resultant force equal to 0. That means resultant force equal to, okay, since I have R there, this one I change to N. I don't want the same alphabet to confuse. I change to N, normal reaction. Normal reaction minus F1 minus F2 is equal to 0. Resultant force is upward forces minus downward forces equal to 0. So because of that, I get upward force equal to downward forces. So that is number 1. Number 2 is resultant moment. Resultant moment, which is clockwise moment. Clockwise moment is F2 D2 minus anti-clockwise moment, which is F1 D1 equal to 0. And because of that, I rearrange it. F2 D2 equal to F1 D1. Okay, so that is the principle of moments. So equilibrium means resultant moment equal to 0, which is fulfilled over here. So example 2. Sometimes you have more than one clockwise. These two are clockwise. This is anti-clockwise. So basically, it works in a similar way. Then you can see sum of anti-clockwise moments, but we have only one. F1 times D1 is the moment, anti-clockwise moments. Clockwise moment, we have F2 D2, F3 D3. You have to add up. So they are equal. Okay. Now, let's see example. A student has a uniform meter ruler. A meter ruler, that means the length is 1 meter, okay, or 100 cm. Of weight 1.20 Newton. So when they say uniform, that means the weight will act at the middle of the ruler. Okay, so let's say you have a ruler of 1 meter, 100 cm, 100 cm. So you should expect the weight to act in the middle because it's uniform. So the point where the weight act is the center of gravity, which is 50 cm. 50 cm from either side. So 1.20 Newton. This is the weight. He attaches a weight of 1.50 Newton at the 10.0 cm point. You know, meter ruler is 0 to 100 cm. Okay, 10.0 cm. So somewhere here. 10.0 cm. So at this point, he attach a weight. Okay, so we put a weight here. Okay, so this object has a weight of 1.50 Newton and places the ruler on a knife edge. He adjusts the knife edge until the ruler balances. Okay, so you have to balance the ruler by using a knife. Deduce the position of the knife edge. Okay, so imagine if this is the ruler, right? So if you are having an object here, it will make the ruler go down from this side. So it goes down from this side. So you want to balance it, you have to put your knife somewhere here to balance it. So you cannot hold your knife upwards there. Okay, so or else it will bend more on this way. Okay, so we have to put the knife edge somewhere here to balance. And let's say this is our knife. put it somewhere here, and you have to find out the position. So I call this X. Okay, so I'm looking for X now, X cm. That's the knife. Okay, so in order to do this, we use clockwise moments, sum of clockwise moments. Okay, sum of clockwise moments equal to sum of anti-clockwise moments. So first of all, we need to recognize the pivot and the position of the pivot. Okay, so the pivot should be the knife itself. And the knife itself should be the pivot. Okay, so this is the pivot. Okay, then the weight of the ruler is clockwise. The weight of this object is anti-clockwise. Okay, so now we have to do the calculation based on this formula. Clockwise moments, we have 1.20, the force, multiply with the perpendicular distance to the pivot. So here to here, 50 minus x. Anti-clockwise moment, so we have the weight 1.50, multiply with the perpendicular distance, which is 10 cm, x minus 10, because here to here is 10. So x minus 10, then you get this distance. So x minus 10. Okay, then we just solve the equation. 1.2 times 50 is 60, minus 1.2x, 1.5x, minus 15. Then 75, 2.7x, and we can get x 27.8 cm. So we get the position of the knife. We must put it at 27.8 cm of the meter ruler. Okay, so this is one question on moment. So let's move on. We look at the next subtopics. Okay, now 4.3, density and pressure. Okay, so density of a material is its mass per unit volume. So we take mass divided by volume, and it's a measure of how compact a substance is. Okay, so how compact a substance is. If it's very compact, then it sinks in water. If it's not that compact, it's low density, then it floats. So the idea is like that. Now, you can calculate density using the following equation. Rho, and this symbol, it looks like P, but it's actually rho. Rho equal to mass times volume, where m is the mass of the object and v is its volume. So this is the formula. Pressure P. Now this is P, this is not rho. P, rho. P and rho. And so this is P, this is rho. Okay, so P, pressure P, is defined as the force perpendicular to a surface per unit area, and can be calculated using the following equation. So again, you see the force and the area must be perpendicular. Something like the moment and talk just now also must be perpendicular distance, but this is perpendicular with the area. So for example, let's say this is the area. The force has to be the perpendicular force. Perpendicular, and then pressure equal to force over area. But in case if the force is not perpendicular, let's say it acts in this particular direction, theta force. So the area is A. Then you want to find pressure, right? You must find the perpendicular component of the force. That means you have to resolve it. You have to find this. This is the perpendicular component of the force. So this is the force given. Now you want to find this. So this is the opposite of the angle. So you have to use sine F sine theta. For our case, F sine theta. So pressure equal to F sine theta over area. So of course, you must be flexible. Sometimes they give the angle here, theta. They give the angle here. Okay? If they give the angle here, then you have to know that, let's say the force is here. This is the area. This is the force. Okay, so you have to resolve. For this case, you resolve this way. So to find the perpendicular component of the force, so we use adjacent. Adjacent means you use cos. So that is F cos theta. F cos theta. If the theta given is in that way, is F cos theta, then the pressure is F cos theta over A. So must be perpendicular no matter how. Sine or cos depends on information given. Okay, so now using the defining equations of pressure and density, you can derive the formula pressure equal to change in pressure equal to change in height times rho, the density, multiply with the G. So this is the pressure in liquid. Okay, or pressure in fluid. So pressure in fluid, we use this one. So sometimes we just put like P equal to H rho G. So the pressure in fluid, we discussed just now. Consider a beaker containing a fluid of density rho and a small cylinder as shown in the diagram to the right. So you put this under the water. The pressure on the bottom face of the cylinder, and this one I discussed just now, which has area A, is due to the weight of the column of the fluid above it. So it's this column of fluid. Okay? So that causes the pressure. You can calculate this mass of this fluid by multiplying its density by its volume. So volume equal to A times H. Mass equal to density times volume. And then as weight equal to mg, you can calculate the weight of this fluid as shown below. Weight equal to mass times g. And finally, you can calculate the pressure using the equation shown above. Pressure equal to weight over area. So the weight divided by the area, and then you get the formula. I normally call it H rho G. So they use rho Hg. It's okay, man. Rho Hg, rho GH, H rho G. It's just the same thing. So they are able to derive the formula. So derive the formula by using these steps. Okay. So therefore you get this formula, and now you can use the equation above to calculate the pressure exerted by a fluid on an object when you know the fluid density and the height of the object, the height of the fluid above the object. This equation does not give you a value of total pressure. It's not total pressure, it's just pressure at the bottom of the surface or pressure on the top surface. Okay, so for example, a stone is thrown into a lake and sinks to the bottom 15.0 meter below the surface. The density of the lake water is 997 kg per meter cube, and the atmospheric pressure is 1.01 times 10 to the power 5 Pascal. So we need to consider the atmospheric pressure also to get a total pressure experienced by the stone. So that means total pressure is H rho g plus atmospheric pressure. That is the total pressure. So first we calculate the pressure exerted by the water using H rho g. H rho g. So you can see they are using that. They put rho g delta H. So the rho is this one, 997. Yeah. G 9.81. The H is 15.0 meter. How deep is the stone? Okay, next find the total pressure by adding up this value with the atmospheric pressure, and then you get the total pressure. Okay, now this one is what we discussed just now. So the top surface and the bottom surface. Bottom surface H2 rho G. The pressure is H2 rho G, but they rearrange it to find the force. So force equal to pressure times area. So that's why the pressure 2 is H rho G, then you multiply with the area. The top surface, H rho G. We use H1 rho G to get the top surface pressure. Then the force is pressure times area. So that's why there's an A there. And then the upthrust. This is what I discussed. Upthrust equal to F2 minus F1. F2 minus F1. You see F2 they draw longer, showing that it's a greater value. Of course it's greater because H2 is greater, right? So F2 minus F1, then you get upthrust. Okay, so Archimedes principle state that the weight of the fluid displaced by a submerged body equal the upthrust force exerted on the body. You know upthrust is this one, right? F2 minus F1. Then it is also equal to the weight of the fluid displaced by the submerged body. So which means you put a cylinder in the water. So this volume of space is originally water. And now, because you put the cylinder inside, the water has to go elsewhere. So we call it water displaced by this cylinder. So the water displaced by this cylinder, of course, has the same volume as the volume of cylinder. And you want to find the weight of that volume of water. That will be the upthrust. So the upthrust is F2 minus F1, which is from here. The upthrust is also the weight of water displaced. Okay. The upthrust is also known as the buoyant force. Buoyant force is also the upthrust. Buoyant force or upthrust. Okay, so weight of water displaced, how to find? So rho GV, rho GV, rho GV, weight of water displaced. The V is the volume of cylinder. You know, like what I mentioned just now, the volume of water that have to go elsewhere is same with the volume of the cylinder. Because the cylinder take up the space and then the water has to go elsewhere. So that is the volume of cylinder. Volume of cylinder is equal to volume of water displaced. Volume multiplied with density. Volume multiplied with density is mass. It's mass. So this density must be careful. It's not the density of the cylinder, it's the density of the water. It's the density of water. Density of water. Because we are counting the weight of water, so we have to find the mass of water multiplied with G. So volume multiplied with density of water, not the density of cylinder. Now you get the mass of water. Mass of water. So this multiplied with this, you get the mass of water. To find the weight of water, mass times G. Mass times G, W equal to mg, right? So you get the weight of water. So at the end, if you relate these two, F2 minus F1 equal to rho G V. So we have a relationship here and there. And at the end, you get the buoyant force. Okay, so that's the thing. And we finish up already. Okay, let's go through questions. Okay, we discuss this straight away. Drag force. The drag force Fd acting on the sphere moving through a fluid is given by the expressions Fd equal to kpv squared. Drag force formula. Okay. Drag force is viscous force. That is what we heard just now. And I also call it air resistant. And that time we also discussed about it is affected by the velocity of the object. If the object is moving faster, the air resistance is faster. So you can see the velocity is there. The speed of the object will affect the drag force. K is a constant, P is the density of the fluid. The fluid can be liquid or air, depends on where the object is. V is the speed of the sphere. Determine the SI unit, SI base unit of K. So this is the front chapters. So I rearrange the formula. K equal to drag force over density velocity square. Okay, then I consider the unit of each of these. Newton. Drag force is Newton. Density is mass over volume, so it's kg. Meter -3. Velocity is meter per second, and a square. Okay, then I know force equal to ma, right? So I can predict the unit to be, because force equal to ma, force equal to ma. So kg ms -2. Kg ms -2. I change to base unit. So at the bottom, I expand this. Kg m-3, m2 become m-1. Then s-2. Then you cut the kg also. M divided by m-1, so become m squared. So that's the base unit of K, m squared. Okay, now we move on. A ball of weight 1.5 Newton falls vertically from rest in air. From rest. So imagine initially it is rest, no velocity, no drag force. Initially only weight act on the ball. Okay. Then the ball is starting to move faster and faster, then the velocity causes the drag force. So the drag force acting on the ball is given by the expression in A. The ball reaches a constant terminal speed of 33 meters per second. So this seems like what we learned in the previous chapter also, terminal velocity. Assume that the upthrust acting on the ball is negligible. So no need to count upthrust. So what kind of upthrusts are they going to be? We are not going to care about that. If you want to count it, then you have to use the Archimedes principle. The A displaced by the ball, the weight of the A displaced by the ball is the upthrust. We are not going to count that. Ignore it. Don't need to use Archimedes principle. Assume it's not there. And that the density of the A is uniform. Okay, so let's move on. For the instance when the ball is traveling at a speed of 25 meters per second, this is not terminal velocity yet. This is terminal velocity is 33. This is 25 only. Determine the drag force Fd on the ball. Drag force. Okay, so in order to find the drag force, okay, so we need to look at the formula. Okay, so the formula is given just now. Drag force equal to K rho V square. K rho V square. Okay, I do it up here for part 1 since the space is available here. F equal to K rho V square. Okay, so you want to count drag force, you want to use this formula. It seems like we don't know the K yet. We don't know the K yet. We don't know the density also. We just know the velocity. How to put the velocity 25 inside to count the drag force? It seems like not enough information yet because we don't know K and rho. We don't know this yet. So we have to make use of the idea of terminal speed of 33 meters per second. Yeah, 33 meters per second. We need to know that at terminal speed, weight equal to drag force. Imagine your ball have weight 1.5 Newton, then it is balanced by the drag force, which must be 1.5 Newton also. When the force is balanced off, then the net force is W minus Fd, right? You get 0. Then net force equal to ma, right? So when this is 0 and this is 0, no acceleration, that is terminal speed. So this is the thing that you need to know. Okay, so if you know this, then how? We know the drag force is 1.5 Newton. At terminal speed, the drag force is 1.5 Newton. So we know that when drag force is 1.5, velocity is 33. So this terminal speed concept leads us to this pair of information. Drag force 1.5, terminal velocity 33. Then we can substitute into the formula to find out the K rho. 1.5 K rho V is 33. 33 square. We at least we cannot find K and rho specifically, but at least we find out the value of K rho. Okay. We can't find it individually, but we just find out the product of K rho. So K rho is 1.5 over 33 square. So we just leave it like this. Or you can change the decimal number where you may lose. If you round off, you may lose some values. Okay, so you may lose the accuracy if you round off. Okay, so just leave it like this. We get K rho already. K is a constant. Rho is also a constant because they said density is uniform. So same density all the time. So the constant is this value. Okay, now we reuse the same formula. Fd equal to K rho V square. Okay, so I put in blue color. And V equal to 25. K rho equal to 1.5 over 33 square. Find the Fd. Okay, so how to do it? Fd equal to K rho V square. K rho is 1.5 over 33 square. The current V is 25. 25 square. Then we can get the corresponding drag force at this particular speed. Okay, so we just multiply. Then you will get 1.5 over 33 square times 25 square. 0.861. So that is the working. Two part. First part is the red one. Second part is the blue one. So two parts.
Like that, I mean 2 marks.
2 marks, yeah. A lot of explanation. You know, during exam, who care about the explanation? Just write down the working and and get the answer. Okay, 2 marks. The acceleration of the ball. The acceleration of the ball. Okay, now to find the acceleration of the ball at this speed. So imagine the ball have weight of 1.5 Newton. At this particular speed, the drag force is 0.861 Newton. So we use net force equal to MA, Newton second law. So to find the net force, 1.5 minus 0.861, the M. Let's see what they give for the mass of the ball. They give the weight of the ball. So as we know, weight equal to mg. Mass is weight over g. Weight over g. Mass is weight over g. So the mass is weight 1.5 over g, 9.81 times A. And then we just count the A. Okay, so let's solve the equation, find the A, you get 4.18 ms negative 2. 4.18. Okay, so that's the acceleration.